Hi and welcome to module 5.11. We have come a long way since the bare bone definition of a filter, and it is now time to put to use everything that we've learned before and build a real-time signal processing system on your PC. So here we will review the technicalities involved in implementing real-time processing on a general architecture, and then we will review the code that will allow you to implement real-time guitar effects on your PC. I hope you're going to have fun with this one. Hi and welcome to module 5.11 of Digital Signal Processing. In this module we'll talk about real-time signal processing with a particular focus on general-purpose architectures such as your PC. We will first examine how data transfer takes place between your PC and peripherals such as the sound card. We will talk about multiple buffering, which is a technique to ensure smooth data communication between the CPU and the external devices. We will look at the general implementation framework from the point of view of the API, and then we will look at how to implement some guitar effects in real time. When we talk about real-time signal processing, we indicate a situation where the maximum time that we can spend to process one sample is indicated by a system clock of period TS. We haven't really talked about sampling and interpolation. We will do that in the next module, but you already know that to process a real-world signal, we will have to record that in the form of samples, and we will record a sample every TS seconds. Then we will process this sample in a causal filter because we are in a real-time situation, and the maximum amount of time that we can spend on the processing of one sample is again TS seconds. And then every TS seconds we will have to play out the output sample. So everything needs to happen in most TS seconds. Let's look in more detail at the output process. We have a series of samples, X of n. We have a sound card, which is the device that will bridge our digital world to the analog world of the loudspeaker, and the sound card operates with a system clock of TS. Now let's assume that our sequence X of n is generated by some algorithm by a central processing unit. On a dedicated audio device, we could use the same system clock to drive both the production of sample and the output process. So the system would be rather simple. Now, on a PC, on the other hand, the CPU works on a clock that is completely independent of the sound card clock. As a matter of fact, it's a clock that is much faster than the clock you would find in your sound card. So the situation is the following. The CPU will generate samples at its own pace and put these samples in memory. The sound card, on the other hand, will fetch the samples from memory at its own pace, which is dictated by its clock, and then output them to the loudspeaker. The transfer of data from the CPU to memory happens via a standard memory bus transaction. The transfer of data from memory to the sound card takes place in the form of a DMA transfer. DMA stands for Direct Memory Access. In other words, the sound card does not need to invoke the CPU in order to access the data in memory. And so this transfer and this transfer, they can happen asynchronously. The problem, of course, when you have two asynchronous processes is how you have them communicate. In particular, how does the sound card tell the CPU that more data is needed? This problem is solved by having the CPU issue an IRQ, an interrupt request to the CPU, and when the CPU receives this signal, it will put another batch of data in memory for the sound card to access. Now, if we were to interrupt the CPU every time we need a new sample, there would be too much overhead. So the idea is that the sound card will consume a chunk of samples already in memory, called a buffer. The sound card will notify when the buffer is completely used up, and the CPU will fill a new buffer for the sound card to use. The key point here, since we're talking about real-time signal processing, is that the time it takes for the CPU to fill up a buffer needs to be strictly less than the time it takes for the sound card to consume that buffer. Of course, the buffering operation introduces a delay, but this delay is a price we need to pay on a general-purpose architecture because we cannot guarantee that the CPU will always be available exactly at the time when we need a new sample. So by processing the data in batches, we insulate the data generation process against concurrent demands on the CPU. Let's look in more detail how this works. This is an example of double buffering. The buffer is the strip here, which is a set of contiguous locations in RAM, say L locations for L samples. The CPU will write the newly computed samples into this buffer, and the sound card will fetch the samples from this buffer for playing. There are two pointers into this buffer. There is a write pointer used by the CPU to identify the next memory location into which write in new samples. And there's a read pointer used by the sound card to identify the location from which the next sample has to be fetched. The pointers are initialized as such. We assume that the buffer has been filled with zeros, say, in the beginning, and we position the read pointer at the beginning of the buffer and the write pointer at the midpoint of the buffer. And now the dance begins. The sound card is started, and the sound card will start fetching samples from the read buffer and move the read pointer in this direction. At the same time, the CPU will start writing samples into the buffer, and it will move the write pointer in this direction. Remember, the key is that the CPU writes sample faster than the sound card reads them. So as time progresses, you can see that the read pointer advances, but the write pointer advances faster. And after a few milliseconds, the CPU will have filled the second half of the buffer and it will stop. At the same time, the sound card will continue reading, and when it reads the entirety of the first half of the buffer, it will signal to the CPU that this part of the buffer is now depleted before moving on to reading samples in the second half of the buffer. When the CPU receives the IRQ, it knows that it will have to start filling the first half of the buffer. This is a circular buffer, as we have seen in the previous module, so the pointer will be rolled around and the CPU will start writing samples here. So the reading process continues at the same pace as before, and now the filling process continues on the first half of the buffer at a faster pace than the reading process. And so again, the CPU will have filled the first half of the buffer while the sound card is still reading the second half. When the second half is depleted, a new IRQ will signal to the CPU that the second half of the buffer needs to be filled again, and so on and so forth. Double buffering introduces a delay that is equal to the system clock times half the length of the buffer. If the CPU is not fast enough, the read pointer of the sound card will trail over memory cells that contain invalid samples, old samples, and we will have a situation of underflow. In practical application, it's common to use multiple bufferings instead of simple double buffering. In this case, the buffer is divided into sub-buffers, and an IRQ will be emitted every time the read pointer trails one of the boundaries. The advantage is that the CPU will be called more often, and so the load on the CPU will be better distributed in time, while still affording a reasonable underflow protection. So far we looked at the output process of the sound card. What about the input? The input is really symmetrical. Instead of having the sound card fetch sample from memory, we will have the sound card put samples in memory and notify the CPU that a new buffer is available for processing. The CPU will work at its own pace. It will share the RAM with the sound card. The sound card will both place input sample in memory and fetch output samples to play, and will signal to the CPU when either of these buffers are empty. Very quickly, the roles are reversed. If this is the buffer in RAM, we now have that the write pointer belongs to the sound card and the read pointer belongs to the CPU. We assume, as per usual, that the initial buffer is filled with 0, and we start the system. The CPU will start getting samples from the buffer, and the sound card will start writing samples to the buffer. The CPU will be faster, and so it will deplete the buffer before the sound card has finished filling the other half of the buffer. When the sound card has finished filling the first half, it will trigger an IRQ, and the CPU will know that this buffer is now ready for consumption, so it will roll the pointer and start fetching the data and process it, and so on and so forth. We now need to put it all together. So we will have an input buffer and an output buffer. We will use a multiple buffer strategy, say with 3 sub-buffers. we will select the buffer sizes and the number of subbuffers to be the same both for input and output, and we will use the input IRQ to drive the processing. This is the input buffer, and so the sound card will place samples into this buffer as they come from, say, the microphone. This is the output buffer, and so the sound card will fetch samples from this buffer and play them through the loudspeaker. Assume that the buffers are zero filled. Since the clock for the sound card is the same both for input and output, the input buffer will be filled at the same rate as the output buffer is emptied. After a few milliseconds, the first chunk in the buffer will be filled, and conversely the output buffer will be emptied. An IRQ will be launched, at which point the CPU will intervene and start processing the input samples, say filtering them, and placing them in the corresponding chunk of the output buffer for later use. Again, the CPU will have to perform this operation faster than the time it takes for the sound card to fill a chunk of the buffer. So here, for instance, when the sound card has filled, say, a third of the next buffer, the CPU is done with the processing. It will mark the input subbuffer as used up and the output subbuffer as ready for playing. The process continues. The sound card is still filling up the second chunk of the buffer, and when it's done, it will launch an IRQ, and the CPU will start processing this input chunk into this output chunk. The processing requires less time than the sound card needs to fill the third part of the buffer, and when the third part of the buffer is filled, an IRQ will be triggered, pointers will be rolled around, and the sound card will start outputting the first chunk of the buffer that was processed earlier, while the corresponding chunk of the input buffer will be filled with new input samples, and the process repeats. The total delay of the system is equivalent to TS times the number of samples in the buffer, because of how we position the read and write pointers. We usually start the output process first, because it doesn't matter if the input trails a little bit, and buffers can be collapsed. In other words, the computation can be done in place. Okay, so how do we do this in practice? We get our PC, and one strategy is the low-level strategy. We study the sound card data sheet. Each chip is different. We write code to program the sound card directly. This will require us to write some particular values to some particular I/O ports. We need to write an interrupt handler, and we need to write the code that handles the data. It's certainly interesting, but very time-consuming and not very portable. The high-level strategy is to choose a good API that allows us to attack the functionality of the sound card without worrying about the details of the implementation, and just write a callback function that handles the data when we are notified that a new buffer is available. Let's look at an example of a typical callback prototype. We will use C in our next examples. And this callback will take simply three mandatory arguments: a pointer to the input buffer, a pointer to the output buffer, and the length of said buffers. So for example, we could write a callback that does simply a cast to convert the generic pointers to the buffers into the right data type. In this case, we choose to use floats. And then a simple loop that for each sample in the input buffer calls a processing function and stores the result into the output buffer. So now the question is, what do we put into the processing function? So let's expand that, and let's define a generic processing gateway. If we're going to use filters, we will need to put in place buffers to store past samples of the input and of the output. So we do this here on this left part of the panel. As we said before, we decide to use floats. So we define a buffer of a certain length, and we choose a power of 2 for convenience so that the circular buffer can be rolled around with a simple masking operation. So we define two buffers of equal length and two indices into the buffer. The processing function will take the current sample. It will store the sample into the input memory. It will call a function that we call effect, because we're interested in implementing guitar effects, that will compute the current output. It will store the output in the memory for the output samples, and it will update the indices into the buffers with the usual circular strategy. So we increment the pointer by 1, and then we roll around the pointer by binary masking. And the processing function will return the current output sample that, as you remember, will be put in the output buffer of the sound card. So let's look at the simple effects that we can generate with this programming paradigm. An echo is a situation where you have a sound that bounces back and forth between two reflecting surfaces. And a simple simulation is given by the following impulse response. You have the original sound, and then you have a first reflection after n samples, and a second reflection after 2 n samples. So you have equally spaced replicas of the signal, which we scale by different weights in order to simulate a decay in time. So we have the original signal scaled by A is usually 1, a first reflection scaled by B, and a second reflection scaled by C. And then we normalize the sum of reflection by the sum of the coefficients in order to have unit gain. To implement this in our framework, all we need is a straightforward translation of the transfer function into C code. So here we define the 3 coefficients that we use for the 3 replicas of the signal, the normalizing coefficient, and the delay between replicas, which is here expressed as a function, of course, of the sampling frequency. The output value is simply the weight sum of 3 delayed replicas of the input. Acoustically, a simple echo sounds like this. First you will hear the original sound, and then you will hear the same sound processed by the simple echo. The simple echo has 2 drawbacks with respect to a natural echo. The first one is that it has only a finite number of repetitions, whereas in a natural situation you would have a theoretically infinite number of back and forth reflections. The second drawback is that each repetition is just an exact replica of the original sound, simply scaled in amplitude, whereas the reflection process in a natural echo would introduce a low-pass characteristic in each reflection. To obtain a better echo, we can go back to our old friend, the Karplus-Strong algorithm. If you remember, the Karplus-Strong works by building equally spaced replicas of the input signal to produce the output. The fact that the input signal is finite support prevents overlap between the output copies, but if we input a standard sequence to the feedback loop, we will have overlapping replicas in time. So the feedback loop already takes care of the fact that we want an infinite number of repetitions in the echo. In order to introduce the low-pass characteristic of a natural echo, we simply introduce a low-pass filter in the feedback path, and the output at this point can be expressed as the usual decay factor times the convolution of the output and the impulse response of the low-pass delayed by capital M plus the input. If we choose a simple low-pass such as the leaky integrator, we can actually write the constant coefficient difference equation, which turns out to be like that. And if we compute the impulse response numerically, we get something that at each repetition of the period of the echo gets smoother and smoother, which is really what you obtain if you apply a low-pass filter repeatedly. The implementation in our processing framework is once again very straightforward. We just need to convert the constant coefficient difference equation to C statements. We define the decay factor, the lambda factor for the leaky integrator. We define the normalizing factor that will preserve unit gain, and again, the echo delay as a function of the sampling frequency. And then we return the output as a linear combination of input and output samples. If we now play the same clip as before through this natural echo, it will hopefully sound better and more realistic. So here is a comparison between the two. The next linear time invariant effect that we will consider is reverb. Reverb is really the superposition of very, very many echo-like reflections that come from different directions and therefore have different delays and different type of attenuations associated to them. Because of the complexity of the impulse response associated to reverb, precise simulations are very costly in terms of computational power. But if we want to just approximate the reverb as would be generated by a very small environment with highly reflective surfaces, we can get away by using a simple all-pass filter, as shown here. Remember, the all-pass filter is a filter whose magnitude response is unit over the entire -pi to pi frequency axis. By appropriately choosing the parameters alpha and capital N in the all-pass, we can obtain a phase response with the staircase-like characteristic shown here. This phase response will introduce different delays to different frequency regions, thereby simulating a multifaceted reflective surface. The implementation of the all-pass filter is again extremely straightforward. We only have two parameters to choose, and then we just implement the custom coefficient difference equation in C. We can now try to apply the reverb to a little guitar snippet. We will play the original and then the processed signal. Let's now look at some very common guitar effects that do not belong to the class of linear time invariant filters. This is to give you an idea that there is a whole world out there beyond linear processing that is very, very interesting. The first type of effect that we will consider is the distortion. Simple distortion can be achieved by truncating a scaled version of the input signal and bringing back the signal to the original amplitude. Tremolo is an effect achieved by multiplying the input signal by a slowly varying sinusoidal component. This will change the volume periodically in time. Flanger is obtained by summing a signal to a delayed version of itself and by varying the delay in time, usually according to a sinusoidal pattern as well. When you sum a signal to a delayed version of itself, you obtain some spectral nulls in frequency. By changing the delay, the spectral nulls will change their position in time, and this will give rise to a variety of effects from, say, a robotic sound to an artificial chorus. From the point of view of implementation, the fact that these effects are nonlinear doesn't really complexify the associated code, and this is really one of the strong points of digital signal processing. We can easily move beyond the standard filtering paradigm without incurring much complexity. So distortion simply takes the input signal, operates a hard limit, and rescales the output. And it sounds like this. Tremolo requires you to define the speed of the modulating sinusoid, and then the output is obtained simply by multiplying the input times an appropriately scaled sinusoid. Tremolo sounds like this. Finally, with flanger, we need to define the maximum delay, the frequency at which this delay will oscillate around its mean value, and then we compute the instantaneous delay by converting to an integer the product of the maximum delay times the oscillating component, and we sum the two delayed versions of the input.